my name is Przemysław Narowski from Warsaw University of Technology. And firstly, I would like to say that I'm really glad that we can meet together today during these insecure times, and that we have an occasion to talk a bit about injection molding simulation and all advances in the technology in the field. Today I would like to show my few remarks about the optimization of filling imbalance in geometrically balanced injection molds. And let us begin. That's the agenda. So firstly, we'll need to know what kind of mold filling imbalance we're going to talk about. And after that, I will just show some brief information about the idea of optimization of the problem, of the issue of mold filling imbalance. And of course, I will show some results from 3 different methods. From the response surface method, which is of course the most tedious one here in this set, because it needs a lot of trials, a lot of simulations. Usually it needs to have this whole central composite design built, and yeah, it's always a lot of work and a lot of time to fill the whole experiment matrix for the method. And of course, the next one will be the Taguchi method, which is fully embedded in Moldex 3D software, and this one is much more easier to done. You don't need to make all of these experiments. This Taguchi array is usually not so broad like this central composite design, and like I said, it's almost fully automated and embedded in Moldex 3D. The last one is so-called brain construction algorithm. It's a method based on artificial neural network systems, self-learning ones, and of course the last one is the most sophisticated one and probably also the most expensive to do, because you need to buy you always need to buy some kind of external software and run the whole procedure in it. But hopefully it's not so hard to understand and quite user-friendly. And of course, at the end, I will just try to draw some conclusions from all the topic from today's presentation. Okay, so probably all of us know that we have at least 2 of different runner layouts in our injection molds. The oldest one, I think, is the older one. Perhaps not the oldest, but the older one from the H type is so-called fishbone layout. And what is typical about this fishbone layout is that the flow path from the sprue to different cavities are not equal. The length is different. We can see clearly here that the length of the first cavity is much shorter than the length of the flow path to the last cavity, and that's of course the reason of mold filling imbalance if we are not making any kind of so-called rheologically balanced runners, so without changing the diameters of the runners, of the gates, and so on. And the other one is of course this H-type runner, which has been developed to have fully geometrically balanced molds and to achieve the exact length, the equal lengths of the flow path to the different cavities. The exact equality, I would say, of the length. And the first layout, the fishbone, like I said, is a obviously imbalanced one, because if we make a shorter sample, we receive such a pattern. So the inner cavities are always fill always faster than the outer ones, and it is and it was possible to simulate in Moldix 3D and in other softwares from I think almost from the early beginning of the technology, because like you can see from the logo here, this is a result, a picture from a quite I would say old version of Moldix 3D. I think it has a 10 years old, at least the picture here on the left. And of course, it is 2.5D mesh here in this specific model. But we have our H-type runners, our geometrically balanced molds, and because they are balanced, the filling should be also balanced. And as we can see, probably all of us have already seen from different molding trials, that in some cases it isn't so. Sometimes the inner cavities, sometimes the outer ones, feel faster than the other ones. So we have a clearly seen imbalance of filling of our cavities, which of course isn't a good thing here for the quality of our parts. And like we see on this picture, in this older version of Moldix 3D and other softwares, and for this 2.5D mesh technology, it was impossible to simulate this mold filling imbalance. Right now, I think since 2005, it is fully possible to do it in Moldix 3D and in some other softwares, but of course it requires a bit of knowledge, a bit of special modeling of the whole system, and of course not every software is available to do that, to simulate this mold filling imbalance. If we draw the flow path along which the polymer flows fastest, has the greatest velocity, and we have more than 8 cavity mold, for example a 16 cavity like this one, we'll see that the path of the fastest flow tends to draw a spiral, a line that is a curve that is somehow similar to the spiral, and that's the reason it is often called the whole mold filling imbalance phenomenon. It is also called a spiral effect. It can be clearly seen here on these two pictures on the right, when we have a mixture of two materials, two polymers, which have different viscosities. To be exact, they have different thermal sensitivity on the viscosity. So the change in the viscosity is less or more dependent on temperature. As we can see here, this less viscous material tends to stick to the core of our runner and fills faster the outer cavities, and this less viscous one, this transparent one, is more situated more closely to the walls of the runners and fills the inner cavity first, and also it fills the inner side of the inner cavity also in a faster manner. Okay, so that was the introduction. Let's move to the point, to the optimization. And to optimize something, we need to have parameters defined of our optimization. And in this case, we have 4 parameters. The first 3 is quite obvious. Yeah, it's a standard of injection molding process. So we have melt temperature, mold temperature, and injection rate. The 2 first parameters were defined according to the material data sheet of the polymer, of the PBT we were molding, and the third one, the injection rate, was just a range of the capability of our injection molding machine. So our injection molding machine wasn't able to inject to have a larger injection velocity than 100 of millimeters per second. That's the reason 80 was the maximum value here. And the last one, which is the only one which isn't an obvious one, is the runner geometry. Namely, we have the values from 0 to 3, and the 0 represents a runner geometry without any net flipper, just a standard runner, a standard branching of runner. The G number 1 is the geometry with 1 net flipper, and of course number 2 represents 2 net flippers on 2 branches of our runners, and geometry number 3 is so-called net flipper max, which is a circular correcting geometry of our runner, which is situated on the end of our sprue in the mold. To assess the severity of our imbalance in filling, we use such a factor of mass filling imbalance, and this factor is positive when inner cavities are filling faster, and it is negative when the outer cavities tends to fill faster. And of course, we need to have our criteria. We have parameters of optimization, but we also need to have criteria. And in this case, of course, we have our factor of imbalance, our IM, which has the largest weight in our optimization. But of course, we are not only aiming to have the fully balanced filling, we also need to produce our parts in economical way. So they need to be cheap enough to sell, and of course, our process it cannot be too expensive. Yeah? So other 3 criteria are strictly connected to the, I would say, to the energy consumption and then the cost of our injection molding process. So injection pressure is quite obvious. Yeah, it's an obvious parameter of our cost of our process, of our energy consumption of the process. But in this case, it has the smallest weight, and of course injection time, which affects our whole cycle time of our process, and the temperature of our part of our molding. In this case, it's just a single measurement, perhaps not a single measurement, is a temperature of a single point on surface of our part, and it has, in this case, it has a weight of 0.2. Because all of these parameters are in different units and in different ranges, we need to normalize them somehow. And we do it like that. When we want to reach the minimum of our criterion, we use this equation, and if we want to reach a maximum volume, we use this one. They are pretty common rules, so I think I don't need to explain them very much. And of course, for our optimization, we need to define the so-called global objective function, which in our case is just a sum of this normalized criterion multiplied by its weights. So it's just a sum of these multiplications. Okay, so now let's go to the results. The first one, like I said, is the most tedious method of optimization, this RSM. And here we can see the result chart of the optimization. The most important thing, the most important value is this so-called composite desirability. So this the global function, I would say, the function of quality for this specific method. And in each window we can see the shape of the curve of this function with respect to specific optimization parameter. So the function from this first window is defined in such a manner. So this is desirability with respect to mold temperature with all other variables, because this function is multivariable, constant, set to the at values which are optimal, and of course chosen by the software. Here in this column we have all components of this composite function, because it's a composite function, so we need to have components, and these components are also so-called desirability function, but they represent only this desirability for the specific criterion of our optimization. So for example, for filling time, the temperature of our part, injection pressure, and of course our filling imbalance. Here is the result of our optimization, so the optimal setting for the process. And of course we made also an experiment, a modeling trial, to check if our simulations are good enough, because like I said on the beginning, all of these optimization procedures were based only on the simulation results from Modelix 3D. So at the stage of optimizing, of building models, generating and acquisition of all this data, we use only Modelix 3D with any other experiments so far. And at this stage, we would just like to check if the prediction of this optimal setting is correct, and it corresponds somehow to the reality. And here we can see the molding from the trial, and it is hard to notice anything specific. We can only say that the tendency is quite right. So we have a small negative imbalance because the outer cavities fill faster, and such a situation is also present here. So these outer cavities fill a bit faster than the inner ones. Okay, so let's move now to this Taguchi method, which is embedded in Modelix 3D. And because it's embedded, we cannot just define our criteria and parameters so freely as it is in other methods, because we have another software for that. Here we need to just choose from the list of specified parameters and criteria which are already possible to use in the software. And here, of course, parameters are called control factors and criteria are quality factors. For the parameters, we were lucky. We were able to choose directly the same control factors as the parameters we choose for our optimization. So we have filling time, melt temperature, and mold temperature. And of course, different runner layouts are different meshes, different models for our simulation. For quality factors and for our criteria, we need to make some assumptions. The first one is that we cannot specify a single point as a quality factor, a temperature of a single point of our part at the end of filling stage. So we just assume that the average temperature of our molding would represent the single measurement, the measurement of the single point in the best way. The other criterion, which isn't directly chosen from the list, which is impossible to choose, is of course the most important one, our mold filling imbalance. And in this case, we decide to assess our mold filling imbalance by the value of standard deviation of the distribution of our density and the end of filling stage. Because as we can imagine, if some cavities fill faster than the other ones, they reach the packing stage earlier, and the density of these cavities, the areas which are inside these cavities, is getting larger. So if we have uniform density distribution at the end of filling stage, we should also have fully balanced filling. And of course, it is possible to choose the filling, the sprue pressure directly from the Moldex 3D list of quality factors. And like I said, it's not so that the method, the Taguchi method, doesn't require so many tests and simulations like the previous one. For the RSM method, 80 runs were needed to reach the result, and here we only made an array of 16 runs. So it's really a time saving and probably also a money saving for the process for the optimization. Okay, so let's look at the result table, and of course we have all our runs and all the results, and the most important one is the last one, our optimal setting. But to analyze it thoroughly, we need to also look at the 3D graphs, and this one is probably the most important one, the most interesting, because here we can see our density distribution in function of two variables, namely the filling time and the melt temperature. And we can see that the larger the filling time, so the injection rate smaller, lower goes our filling imbalance. And of course, the larger the melt temperature, also lower goes our mold filling imbalance. And of course, we can also see that we cannot go too low with our filling time. We cannot inject too slow, because we'll also reach a slight increase in our filling imbalance, because we're also increasing the shear rate, because the cooling effects of the flowing polymer take advantage, and the wall of our runner start to freeze. Okay, here we have the same density distribution, the same mold filling imbalance, but right now, instead of melt temperature, we have mold temperature, and we can see that it is always better to use higher mold temperatures to reduce the mold filling imbalance. And like in the previous case, we cannot inject too slow. We need to find an optimal value of our injection rate. In terms of our temperature of our part, it is quite obvious. So we need to have the lowest possible injection speed, and of course the lowest possible melt temperature. I think it doesn't recommend any explanation. It's quite obvious why is it so. And the same is with the mold temperature. Lower the mold temperature, lower goes the average temperature of our part at the end of the filling stage. But if we analyze the sprue pressure, we also have this I would say classic process window. So we need to find our best injection velocity our best injection rate, to have the lowest value of injection pressure. But the other curvature, which makes the whole saddle here, is a bit strange, to be honest. Interesting, in my opinion. It demands some further investigation, because we have the smallest, the minimal value of our pressure for the high temperature of our melt, but also for the low temperature. And that is interesting, I would say. Yeah? Why is it so? Why for a very low, the lowest possible temperatures of our melt, we have the lowest sprue pressure? But in terms of mold temperature, we see almost a dominant role of the injection time, so of the injection rate, and that still this optimal value determines the best, the lowest sprue pressure. And it also seems that the lower the mold temperature, also this sprue pressure goes down. Yeah. And if we compare our simulation with the reality, we'll see the same tendency. So a small negative imbalance, which is also present on our simulations. Yeah. So we have pretty much good agreement between the simulation and the reality. Oh, please do not consider the whole filling stage, yeah, because here it was a bit this short samples were taken a bit earlier than this simulation. It was something about 80% of the whole filling, of the whole molding, and here it was something about 90. Yeah, it was just calibrated like that because the imbalance is better seen at this stage in the simulation than on that one, because probably of the different volumes here we have in reality and the simulation. Not all, still not everything is considered in our model for injection molding simulation. Okay, so let's now, right now is the last optimization procedure, the most sophisticated, I would say, which requires a specific software to do it. This so-called brain construction algorithm, which is based on, which is honestly some kind of combination between traditional statistics, namely regression model buildings, and these artificial network systems, and it's some kind of patented also procedure and way of building models and optimizing processes. And here we can see this optimal setting and the values of our criteria. This green areas represents the ranges we have specified before for our criteria, for our quality factors. And as you can see, only only this injection pressure, sprue pressure, isn't going to be fulfilled. It falls out of the range for this optimal setting. The other ones are inside of the ranges and only and almost in the middle of it. So it looks like it is really the best, the optimal case for our process. And if we compare one more time, I think we already got used to it, that our simulation looks pretty much like the reality, like the experiment, and this slight negative imbalance is always seen because it was predicted for all types of optimization procedures. all of them predicted that the slight negative imbalance is the optimal one. But let's look at numbers at this point. The most important thing is the right column here, namely the value of the objective function. And here on the left we have, of course, all our three optimization procedures. And if we look for the largest value, because that was the idea, the goal of our optimization was to reach the largest value of our objective function, we'll see that we have the largest value for the Taguchi method, but for the simulation results, because like I said, we based our optimization procedures only on the simulation, and if we take into account only the results of the simulation, the Oscar goes to the Taguchi method. But if we do the same for the experiment, we see that the last method, the one which is based on this artificial neural network system, has the largest value of the objective function. So the results from the experiment, these results showed that that this function is the largest. That means that this is the truly optimal case. Okay, so right now let's try to draw some conclusions. And of course, the first and maybe the not most important one, but I think the most obvious, that it is always good to use optimization. Yeah. The optimization procedure, they always do their work, and it's always better just to optimize something with any method instead of using this traditional trial and error way. From this specific study, we can see that this neural network procedure, this BCA, tends to be the best. It reaches the largest value of our objective function in terms of experiment. However, the Taguchi method, which is, to be honest, the easiest way to perform, you just need to have Model 3D to do it, and it's the fastest one, is really good comparing to other methods, because we need, like I said before, we only need 16 runs to have a value which is comparable, or in this case even better than the value predicted by this RSM methodology. Yeah, which is of course is a great advantage of this DOE with Taguchi arrays. But of course, last and not least, we still need to put more attention of building better, more detailed models of our whole injection molding process. Because like we saw on the table on the previous slide, we see there is a still quite large discrepancy between the simulation and the reality in terms of filling imbalance, because like it was shown on the pictures of which compared to the experiment, the moldings, and the simulation results, the overall picture is almost the same. Yeah? The tendency is the same, and it's hard to notice everything specific. But in terms of filling imbalance, there is still a quite large discrepancy, and I'm sure that if we had used the newest modules, the newest advances of Model 3D, like this machine characterization and 3D barrel, we would have seen different results of optimization. who knows what we would have discovered. Yeah, and that will be all for today. I hope I didn't bore you to death and you are still there. Thank you for your attention. If you need any other guidance on any other information about this whole optimization thing in injection molding, feel free to contact me via this email address, or if you are just want to do it by yourself, you can see you can check all these results from this specific project in these two journals. There are a few papers there. If you just type my name in the search box, you will get everything you want from this specific study. Okay, so one more time, thank you for your time, for being here. Take care, and I hope we will see each other soon in person. Bye.